The following is analysis of Lab 7 on interference by Jared Hout and Emma Landseedel. This is an analysis of Young's double slit experiment. We were given two slits of a known distance apart, and we're trying to test to make sure that that distance is truly what it is. So we have a laser of known wavelength, the slits, and then projected down here, a known distance away, is a screen. We can measure the fringe distance between the spacing between the fringes down here, and using that, this distance, and the wavelength, we should be able to find an experimental value of the slit separation.
Using this formula, we calculated our slit spacing to be 252 microns, and using the RSS with the errors that were given in the lab procedure, we came up with an error of 4.65 microns, and since that gives us a spacing of 257, we can't recommend that we buy these slits.
The purpose of this experiment is to find the wavelength of this laser using Lloyd's mirror experiment. So a point source is made, but then the mirror creates a virtual point source as well. Those interfere, creating an interference pattern similar to Young's double slit experiment. They're registered by the camera, and then the camera inputs an image into a MATLAB program, which allows us to find the pixel separation of the fringes, which we can calculate big delta with. We also know big D by the distance between the point source and the camera, and we know little d, or the change in little d, based on this mirror height, and that gives the distance between the virtual and real point sources.
Okay, so given the formulas that we had in the lab, we were able to differentiate both sides with respect to the big lambda, giving us a formula here. And when you graph the left side on the y-axis and this part here on the x-axis, you get a slope equal to the negative of the wavelength of the laser. And we got a 600 nanometers as our wavelength, and that is really close to the real wavelength of 633 nanometers. The R-squared value for this line was 0.98, really close to 1, meaning our line was very close to being linear. And that means that our individual data points match the trend line. The measurement that was definitely prone to most error was the mirror displacement, because it was such a small value that we manipulated directly. So for this experiment, we used a ripple tank to analyze how spherical or cylindrical waves from a point source interfere. We had a light that was either strobing like it is now or steady, and when it was steady, we were able to see the power flow lines in a hyperbolic pattern. When it was strobing, we were able to see the different wavelengths appear, and we were also able to change the frequency of the waves in order to get a different number of wavelengths.
So as the frequency was increased, the number of wavelengths increased, as you can see by the increased number of power flow lines in here versus here. They form a hyperbolic pattern, you can really see it strongly here, as expected, and in the center they're straight across as also expected. Using the strobe pattern, we are able to see that a shift of lambda by 2 occurred between the in-phase and out-of-phase interference patterns.